Today we will study algebraic integers in quadratic fields, and we have seen that a quadratic field is always of the form q root m, where m is a square free integer. It can be positive, negative, but it is not equal to 1. For algebraic integers, note that if the minimal polynomial is fx, then this fx is a monic polynomial with integer coefficients. This is a consequence of Gauss theorem. See, if we have an algebraic integer, it satisfies some monic polynomial with integer coefficients. But the minimal polynomial also has the same property. So let me just recall that. If alpha is an algebraic integer, alpha satisfies a monic polynomial gx with integer coefficients. If fx is the minimal polynomial of alpha, then fx is monic, fx belongs to qx, and alpha satisfies this gx, and this minimal polynomial will divide this polynomial gx in qx. fx divides gx in qx, that is gx equal to fx into hx for some hx in qx. Now gx is monic and fx is monic, hx is also monic. And gx is a monic polynomial with integer coefficients. fx and hx are monic polynomials with rational coefficients. When we have this situation, Gauss theorem tells us that both fx and hx must be polynomials with integer coefficients. Since gx is monic and in zx, and fx, hx are monic and in qx, by Gauss theorem, both fx and hx are in zx. This shows that the minimal polynomial of an algebraic integer has coefficients in z. Thus, the minimal polynomial of an algebraic integer has all coefficients in Z. That is, all coefficients are integers. This is a fact that is useful in obtaining algebraic integers of a quadratic field. If we have a quadratic field, it is of the form q root m, and we know that its elements are a plus b root m such that AB belong to Q. And if you take the common denominator and call it as C, you can write this also in the form a plus b root m divided by C, where now a, b and C are in Z. Okay. So this is also equal to the set of all a plus b root m divided by C, where a, b, C belonging to Z, and we can even make C bigger than 0. So we have the following theorem. Let Q root m square free integer not equal to 1 be a quadratic field. So what are the algebraic integers? So elements of q root m are of the form a plus b root m by C. Now if C is equal to 1, that is, the element is of the form a plus b root m, that is certainly an algebraic integer. If m is equal to 1 mod 4, m is congruent to 1 mod 4. In that case, you can also have 2 in the denominator. That is a plus b root m divided by 2. This can also be algebraic integers. In that case, you require that a and b both should be odd. Okay. So odd plus odd root m divided by 2. Such a thing is also an algebraic integer. And these are all the algebraic integers in q root m. So then 1 a plus b root m ab in Z are algebraic integers in q root m. Second, if m congruent to 1 mod 4, then In addition, so if n congruent to 1 mod 4, such elements are already algebraic integers. In addition, a plus b root m by 2 with a, b odd integers are also algebraic integers. The third thing is that every algebraic integer in Q root m is one of these two types. That is, if m not congruent to 1 mod 4, all the algebraic integers are of the form a plus b root m. If m is congruent to 1 mod 4, then you have integers of the type a plus b root m and also integers of the type a plus b root m by 2, where a and b are both odd, and this gives you all algebraic integers in Q root m. So we will prove this. A plus b root m, this first thing, let us look at that. AB belong to Z, and then a plus b root m is an algebraic integer. Why? Because a is an algebraic integer, b is an algebraic integer, root m is an algebraic integer, and so b into root m and a plus that, they are all algebraic integers. So that sum and product of algebraic integers is an algebraic integer. Therefore, a plus b root m is an algebraic integer, because a, b root m are algebraic integers, and or we can just find out the polynomial satisfied by a plus b root m. That this is alternative argument, directly find the polynomial. So let me mention that. Or alpha equal to a plus b root m, alpha minus a square equal to b square into m, and therefore alpha satisfies a monic polynomial with integer coefficients, and therefore alpha is an algebraic integer. This is for any m. Second thing is, what happens if m congruent to 1 mod 4? Now consider the following polynomial. X minus a plus b root m by 2 into x minus a minus b root m by 2. Consider this, which is x square minus ax plus a square minus b square m divided by 4. If a, b are odd and m congruent to 1 mod 4, a square minus b square m is congruent to 1 minus 1 into 1, that is congruent to 0 mod 4. This numerator a square minus b square m, if you consider, this is 1 mod 4, 1 mod 4, 1 mod 4. So this is 0 mod 4 means divisible by 4. So if you divide this by 4, you get an integer. That means this a plus b root m by 2 satisfies a polynomial with integer coefficients. Therefore, this is an algebraic integer. Mod 4 and a, b odd, a plus b root m by 2 is an algebraic integer. Now we want to show that these are all the algebraic integers in Q root m. So suppose root m by c is an algebraic integer, start with an algebraic integer and assume that the GCD is 1. Because if there is some common factor, we can just cancel it and have alpha in this form. ABC is 1. Now if b equal to 0, alpha equal to a by c is a rational number, and it is an integer, means an algebraic integer if and only if a by c is a rational integer, usual integer, that is if c divides a, that is if and only if c divides a. So if b equal to 0, then what are the algebraic integers? They are of this form only. They are rational integers, usual integers. Now suppose b is not equal to 0. If b is not equal to 0, then alpha is not a rational integer, not a rational number even. And what is the degree of alpha? It is 2. It is not 1, and degree will be 2. In fact, we can give the polynomial. In fact, alpha satisfies. What is the polynomial satisfied by alpha? So it is easy to obtain it in the following way: x minus a plus b root m by c into x minus a minus b root m by c equal to 0. Okay, this is the first factor, x minus, this is alpha. So certainly if you add something here, additional factor, then this is satisfied by alpha. Now simplify this. What is this polynomial? X square minus 2a upon c plus a square minus b square m upon c square equal to 0. X square, see, these are roots alpha and beta, and sum of the roots is 2a upon c, and the product of the roots is a square minus b square m divided by c square. This is the polynomial satisfied by alpha equal to a plus b root m by c. This is a polynomial, so left hand side is a polynomial with rational coefficients since alpha is an algebraic integer, this is the minimal polynomial of alpha, because this polynomial is of degree 2 and it is a monic polynomial, so it is irreducible polynomial of alpha, and alpha being algebraic integer, the minimal polynomial must be over z. So it must be with integer coefficients. Now if b equal to 0, then also if alpha is an algebraic integer, then this is with integer coefficients. See, even if b equal to 0, alpha being an algebraic integer, c divides a, so this polynomial is with integer coefficients. In this case also c divides a, so putting b equal to 0 you get a polynomial that has integer coefficients. C divides a square. Now this polynomial is satisfied by alpha also. Is satisfied alpha, and if it has integer coefficients, then alpha will be an algebraic integer. Just the other way, that if this polynomial has integer coefficients, now already alpha is a root of this polynomial. So if this has integer coefficients, then alpha will be algebraic integer because it satisfies some polynomial with integer coefficients. So what we have seen here is that if alpha is an algebraic integer, whether b is not equal to 0 or b equal to 0, in any of these cases, this polynomial has integer coefficients. If this polynomial has integer coefficients, then because alpha is the root of this, alpha is going to be an algebraic integer. So we have got a condition for alpha in the quadratic field q root m to be an algebraic integer, and that condition is in terms of coefficients of this polynomial, that alpha in q root m is an algebraic integer if and only if this polynomial has integer coefficients. Thus, for b equal to 0 or b not equal to 0, for alpha equal to a plus b root m by c, ABC in Z, ABC take an element like this, you can always this is an element in this is general element in q root m. Is an algebraic integer if and only if square x is there. I have to write x here. 2a upon c times x upon x plus upon c square has integer coefficients. Now this means this condition can be written as C divides 2A. So that is if and only if C divides 2A and C square divides A square minus B square M. C divides 2A and C square divides now let us show that A and C are coprime. So suppose AC bigger than 1. So let P be a prime dividing AC. Therefore, P square divides C square. So, P square divides A square minus B square M. Okay, P square divides both and P divides both A and C. P square divides C square. C square divides this. Therefore, P square divides this. But P square already divides A square. Therefore, P square divides B square times M. The other term, B square M. But M is square free. Therefore, P has to divide B. P divides B. Even if P divides M, P square cannot divide M. So one P has to divide this B square term. So P divides B. But now P already divides A and C. And P divides B. That means we have got a common factor for A, B and C. Okay. And therefore ABC is not equal to 1. P divides A, B, C. This is a contradiction. Because we are assuming that ABC equal to 1. And this shows that thus AC must be equal to 1. Okay. Now suppose C is bigger than 2. You want to show C is 1 or 2. In the denominator you can either have 1 or 2. Suppose C is bigger than 2. Now C divides 2A. A number larger than 2 is dividing 2 times A. Okay. That means that C cannot completely divide 2 because it is larger than 2. Therefore, there must be something common between A and C. Therefore, AC is bigger than 1. This is a contradiction. Therefore, C is either 1 or 2. C cannot be bigger than 2. C is a positive integer and it cannot be bigger than 2. So it is 1 or 2. So if C is equal to 1, that's what we want. So if C equal to 1, what is alpha? a plus b root m, a b in z. What happens if c is 2? So if c equal to 2, 4 divides a square minus b square m. Look at this property, c square divides a square minus b square m. So 4 divides that, but ac equal to 1, so a is odd. A square minus b square m congruent to 0 mod 4. Now this is odd, therefore this also must be odd. Okay, therefore b square m is odd. Therefore b is odd. Now a square and b square, they are both 1 mod 4. A square congruent to 1 mod 4, b square congruent to 1 mod 4. Square of an odd integer is congruent to 1 mod 4. In this 1 mod 4, 1 mod 4, so what is m? Therefore 1 minus 1 into m congruent to 0 mod 4, that is mod 4. So that is the second case, that if alpha is an algebraic integer, then a be odd and m congruent to 1 mod 4. So that gives you all algebraic integers. That these are certainly algebraic integers and any algebraic integer is of this form. So now let us list these algebraic integers. Thus, so m square free integer that is there. So for m congruent to 2 or 3 mod 4, the algebraic integers in Q root m are, what are they? A plus b root m, a b in z. Whereas if m congruent to 1 mod 4, we have two types of algebraic integers. They can have either 1 in denominator or 2 in the denominator, that's all. No other positive integer can be in the denominator. If, so for m congruent to 1 mod 4, the algebraic integers u root m are of one of the following two types. One, a plus b root m, a, b in z. This is one type. Second type is a plus b root m by 2, ab in z, both odd. Both odd. Okay. These are two types. So depends upon the value of m. What are the algebraic integers? Now these two things we can bring together also. For both of them you can put 2 in the denominator. This can be written as 2a plus 2b root m divided by 2. First thing, 2a plus 2b root m by 2. 2a plus 2b means what? Both this we can consider a and b as even integers upon 2. So that is the form of that algebraic number, algebraic integer. Okay. So these two can be put up together. In other words, for m congruent to 1 mod 4, the algebraic integers are what are they? A plus b root m divided by 2. Now I am putting 2 as common denominator, where AB in Z, first case we say both are even, both even or both odd. Now other way of saying the same thing is following. These can also be written as another way. C plus d times 1 plus root m by 2, where CD belonging to Z. CD belonging to Z. Just see why anything here is here and anything here is here. Suppose A and B are both even, then that number is some integer plus integer times root m. And now you take d to be 2 times d dash, so it is c plus d dash into 1 plus root m. And you can find out c and d dash from these integers in this. This you try to verify yourself, that by solving some equations you can see that any number here can be put in this form and conversely. One more thing here, that is, we have already seen that if alpha beta are algebraic integers, then so are alpha plus beta, alpha, beta and minus alpha. So from this it is clear that from this the set of all algebraic integers in an algebraic number field you take this subset of algebraic integers of a given algebraic number field, then for this subset some product negative is there. That means this subset is a subring of that algebraic number field, is a sub of the given algebraic number field. Itself ring. Set of all algebraic integers is a ring. So the rings here we have seen these elements. If M is congruent to 1 mod 4, such elements they form a subring of the ring of these elements form a subring of the given field Q root M. Okay, it's a ring. It is itself a ring. We shall see some more properties of algebraic integers. One property we will see. This is a proposition. Given any algebraic number, you can multiply it by some integer and we can get an algebraic integer. This is what this proposition says, that alpha be an algebraic number there is C in Z, C not equal to 0, such that C times alpha is an algebraic integer. Proof of this. This is obtained from the polynomial satisfied by the given algebraic number. So, suppose alpha satisfies the following polynomial. Plus a1 alpha raised to n minus plus an equal to 0 with ai as integers and not all 0. Some polynomial is satisfied by alpha. In fact, we can assume that a naught is not equal to 0. So, assume A naught not equal to 0. Now what we do is you multiply by, that will make this coefficient as a naught raised to n and it will match with this. Therefore, a naught alpha raised to n. Now a naught alpha raised to n minus 1 plus, now a2 is there and one a naught will remain, and a naught alpha raised to n minus 2 plus and so on, plus we have a naught raised to n minus 2 a naught alpha plus a naught raised to n minus 1 is equal to 0. A naught alpha raised to n plus a1 a naught alpha raised to n minus 1 plus a2 a naught alpha raised to n minus 2 and so on, plus a naught raised to n minus 2 a naught alpha plus a naught raised to n minus 1 is equal to 0. And this is a polynomial satisfied by a naught alpha. It's a monic polynomial. A monic polynomial satisfied by a naught alpha. This gives a monic polynomial satisfied by a naught alpha. The polynomial has integer coefficients a1, a2, a naught and a naught raised to n minus 2 and a naught raised to n minus 1. That means a naught alpha is an algebraic integer. Therefore, a naught alpha is an algebraic integer. And then you wanted some c not equal to 0, you can take that c to be this a naught. So take c equal to a naught. So given any algebraic number, you can multiply it by some suitable non-zero integer and get an algebraic integer. That is what this proposition says. Okay, we will now study norm of an algebraic integer or algebraic number in a quadratic field. So norm of an algebraic number in a quadratic field. So take alpha k equal to q root m square free integer. Now alpha equal to a plus b root m divided by c, a, b, c in z. We can always find a, b, c in z such that alpha is like this and c is not equal to 0. We may or may not assume that PD of ABC is 1. We may or may not assume that C is positive. Alpha can be written in this form. We have already seen that alpha satisfies a specific quadratic polynomial, and so let me take alpha bar to be a minus b root m by c. Then alpha bar equal to a minus b root m by c is called the conjugate of alpha in q root m. This is just like conjugate of a complex number. A plus ib, conjugate is a minus ib. Similarly we have, here only thing is m can be a positive integer also. A plus, so 1 plus 2 root 2. Conjugate is 1 minus 2 root 2. It is not complex conjugate. It is a conjugate in the field q root m. Okay. Alpha and alpha bar are roots of the same polynomial x square minus 2a upon cx plus a square minus b square m divided by c square. You can say same polynomial equation, this is equal to 0. They are roots of the same polynomial equation. And note that if alpha is an algebraic integer, then so is alpha bar. If alpha is an algebraic integer, then so is alpha bar, because it is the root of the same polynomial. And the norm of alpha is defined as alpha into alpha bar. Norm of alpha in q root m is defined as norm of alpha equal to alpha into alpha bar, and that is a square minus b square m divided by c square. So the properties of the norm we shall see in the next lecture.